This is a presentation on parallel prefetching in Canonical Ensemble Monte Carlo simulations created for the AICHE annual meeting. My name is Harold Wicks Hatch, and I am a permanent staff member in the Chemical Informatics Group and MML of the National Institute of Standards and Technology, an agency in the U.S. Department of Commerce. So, why are parallel algorithms important? Well, the number of transistors and microprocessors continues to increase over the years, but beginning around 2005, the clock speed and single-thread performance hit a plateau. Computers aren't getting faster anymore, they simply have more cores. This means that a single simulation that took a month in 2005 still takes a month in 2020, unless it is parallelized to take advantage of those multiple cores. Before I describe prefetching, I'll briefly review three other parallel strategies. Domain decomposition requires large system sizes relative to the particle interaction range, and domain decomposition is more efficient for whole system updates like molecular dynamics and less efficient for a series of small perturbations as typical in Monte Carlo. Configurational bias is parallelizable, however, advancements like dual-cut configurational bias that are much more efficient unfortunately also decrease the parallel efficiency. And lastly, parallelizing by divvying up order parameter ranges over different processors is another option in flat histogram methods. Now, all three of these can be used simultaneously with prefetching to allow efficient parallelization over more cores than ever before. A serial Markov chain is shown below with two trials. Starting at state A, trial 1 is rejected, so you remain in state A, while an accepted second trial results in state B. In comparison, prefetching attempts a batch of trial perturbations from state A simultaneously, and then reconstructs the serial Markov chain. To do this, when a trial is accepted, the remaining trials must be ignored. For example, trial 2 is accepted here, so trial 3 cannot be used. Thus, prefetching efficiency decreases when trials are more likely to be accepted, and it also decreases when the overhead synchronization takes a long time. On the left is a plot of the diffusion of Lennard-Jones particles as observed by the simulator in real time, as a function of trial acceptance probability. As the number of cores increase, shown in color, optimal efficiency is reached for lower acceptance probability. On the right is a plot of the efficiency as a function of the cutoff, which is a surrogate for the inverse of the synchronization overhead time, again shown for different numbers of cores in color. With minimal overhead, you can get 1.7 times speed up with 2 cores and 3 times speed up with 4 cores. In summary, prefetching can speed up Monte Carlo simulations and is implemented in the open source software called Feast. Preliminary results show that the method is even more efficient in the Grand Canonical Ensemble with flat histogram methods. I'm also looking for 2 postdoc candidates that require U.S. citizenship. Thank you very much for your time.